Hey everybody, today we've got one of my favorite lessons of the unit. It's on refraction. Now whether or not you know what that means, I know you've seen it in action in the past. So here's a glass of water with a straw in it, and you see that straw looks broken with a nice paper towel background. Here's the same glass, now it has a spoon in it. That spoon looks pretty weird, but it's a normal spoon. It looks very large on the bottom, and the top part looks normal. Here's a couple of bears. I like bears, but these bears seem to have a problem with their heads. The head is not located where their body is, so it kind of looks funny. And then we've got this guy. So you know you're in for a good time when you see somebody spell fun with a PH. But all these are examples of refraction. So to get us started here, let's start with the demo.
We're going to look at what happens when light goes from one medium to another. So the first medium I have is air, and the second medium I have is water. I've got this transparent container, filled it with water. I put a little powdered coffee creamer in there, cloud it up a little bit. You'll see why in a minute. You could also use milk, but I thought if I forget to dump it tonight, it might smell tomorrow. This is also a demo that is very easy for you to do at home if you have a similar container and a laser pointer. That's really all you need. A fish tank works great. That's what I use at school. But if you have fish in that tank, do not put coffee creamer or milk in there. Fish don't like it. So for you guys to see this better, I need to turn the lights down. So I'm going to turn the lights down and then we'll go through this. All right, this should work. So when I shine the laser pointer into the water, you can see the path the laser's taking in the water because I've got it clouded up like that. But you don't see the path of light in the air. So to help you see that, I've got a meter stick that I tried to make as visible as I could. And I'm going to line the laser pointer up with this meter stick. So the meter stick will represent the direction the light is going before it hits the water. And now you can see it bend once it hits the surface of the water like that. So it's bending downward, we can say. So air is less dense, water is more dense. The speed of light is faster in air, slower in water. So when you're going from a faster medium to a slower medium, it will bend down like that, or we say it bends toward the normal line. If we have a normal line perpendicular to the surface of the water, that's what we're going to have. Okay, so you can see it bending down towards that normal line. Now, one other thing I want to show you is, I'm going to take the meter stick away, but if I shine it at just the right angle, you can see that's Monica off to the right there. You can see the dot. All right, so that's coming from the surface of the water. The light is reflecting off the surface of the water. So this is another case where, when a wave goes from one medium to another, some of that wave will be transmitted into the other medium, in this case into the water, and some will be reflected off of that surface, in this case off the surface of the water, and hits Monica in the head there. So there's an example of refraction going from air to water.
Now we've seen that light bends when it goes from one medium to another. So now let's talk about why it does that. It has to do with the speed of light. Now we know the speed of light in a vacuum is 3 times 10 to the 8 meters per second, or 300 million meters per second. Speed of light is slower in other materials like water, glass, plastic, things like that. Now, you may have heard that the speed of light is absolute, that the speed of light always goes 3 times 10 to the 8 meters per second, and that is true. I'm not going to get into that right now. Instead, I'll post a link to a video that explains that pretty good. Check that out if you're interested. But for now, we can say that the average speed in different materials is less than 3 times 10 to the 8 meters per second. So we'll go with that. Here are a couple examples here. In glass, it's 2 times 10 to the 8 meters per second. In water, a little bit faster. And diamond is a pretty dense material, and that's where it's going fairly slow, relatively speaking. Now let's get into the concept of this index of refraction. So these numbers being like 10 to the 8 meters per second, they're a little inconvenient to deal with. So there's this factor, this quantity called index of refraction that makes it a little easier to talk about, kind of like the elemental charge or a light year. The index of refraction is just the ratio of the speed of light in a vacuum to the speed of light in that medium. So it's given by this equation, C over V, where C is 3 times 10 to the 8 meters per second. A higher speed means a lower index of refraction. So if you see a lower n value, that means it's going faster than something with a higher n value. Now, one question I always like to ask my students is, what are the ranges of values for index of refraction? Can it be negative? No, it can't be negative. We're just talking about speeds here. How about from 0 to 1? Can it be in that range? Can it be greater than 1? Well, if you think about it, 3 times 10 to the 8 is the fastest light can go. You're not going to get a speed bigger than that. So the denominator at best is going to be the same value, but it will most likely be less than that, which makes this fraction bigger than 1. So yeah, index of refraction generally is going to be bigger than 1. Unless you're talking about a vacuum, then it actually is 1. So why does it refract? Here are 3 pictures. They really show the same thing, but it's just 3 different scenarios. Here are soldiers marching in grass and then they hit mud. Here's a car driving on asphalt and then it hits sand. Here's a shopping cart on pavement and then it hits the grass. So again, they're all doing the same thing. I'll stick with the soldiers. They're on grass. When they're marching on grass, they're going at a good rate. When they hit the mud, they're going to slow down. It's harder to walk through mud. Now, you're only going to see the bending of light when you come in at an angle. If you just go straight in, you will see a change in speed, but you're not going to bend that light. So they're coming in at an angle like this. The first soldier, I'm going to look at this line right here. The first soldier to hit that mud is going to be this guy. And when he hits the mud, he's going to start slowing down. But the other 3 are still going fast. They're still in the grass. And then this guy hits the mud, he's going to slow down, and these guys are still going fast. So what happens is it kind of bends around like this. These guys slow down, and that whole line just bends like that around that curve, so to speak. Similar, let's go to the shopping cart. This wheel is going to hit the grass first. It's going to slow down. This wheel is going to speed up. So it's going to kind of whip around here and change the whole direction of that shopping cart. Now, the same is going to happen. I didn't show this in the demo, but the same thing happens if you're going the other way. So like from mud to grass. Let's look at this line of soldiers here. This guy is going to hit the grass first, so he's going to start speeding up. These guys are still going slow. So you're going to get that bending around this way because this guy's going to be going faster before these. And then once they're all in the grass, they're going faster in that direction. So it's going to bend exactly the same amount. It's just the reverse situation. So we can calculate the amount light is going to bend using something called Snell's law. This is it. Here's the equation. The angles, remember we talked about this with mirrors, always with respect to the normal line, always. It's very important. In this situation, you've got one medium on one side and the other medium on the other side. So my demo, let's say this is air and this is water. It doesn't matter. You can switch them around, but just make sure the air is with the air and the water is with the water, or whatever the 2 materials are. So let's do an example here. All right, we've got a light ray coming in at a 50-degree angle. It's going to hit a boundary, and then it's going to come at some unknown angle here. From what we just talked about, so I'm going to tell you these 2 materials, one is glass and one is air. Now, which one is which? From this picture, we should be able to tell. Imagine that line of soldiers marching down here at the angle. The soldier on this side is going to hit this medium first, and then these soldiers are going to hit it later. So it looks like this soldier has to slow down and these speed up until, well, they don't, I'm sorry, this soldier slows down, these keep going fast, and so it's going to bend around that way. So it looks like we are going from a faster medium to a slower medium. Faster meaning less dense, slower meaning more dense. So this is what we have. We've got a light going from air to glass in this case. Now we can solve for that angle that it's going to take in the glass. What I like to do is I identify which is medium 1, which is medium 2, just so I keep it straight. I don't want to get them mixed up. Then I go right to Snell's law. So medium 1 I've defined as air, medium 2 glass. You could flip those, it doesn't matter as long as you're consistent with it. So the index of refraction for air, okay, technically it's 1.0003. It's very close to the speed of light in a vacuum. But for our purposes, 1.0003, we can call that 1. Index of refraction for glass, 1.52. And I just got these numbers out of a table. If you were solving for this angle, you'd be given these indexes of refraction. Now we just plug things in. Okay, keeping air on the left and glass on the right. We've got 1 for the index of refraction for air. We've got the 50-degree angle, again with respect to the normal. 50-degree angle for air. On the glass side, we have the index of refraction for glass, 1.52, and we don't know this angle. So that's what we're solving for. So we just do the math there. We'll have to do an inverse sine to get that angle, but 30.3 degrees is our result there. What would happen if we have light going from, let's say, water to air, a more dense medium to a less dense medium? We know more dense to less dense. If we think about the soldiers marching in the grass and the mud, it's going to bend away from the normal. But what if we keep increasing this angle, the angle of incidence here? What's going to happen? Well, let's take a look.
Okay, we've got the same setup that we had when we looked at refraction. Now, in this case, I'm going to start the laser from ideally below the surface of the water, but it's got to be outside the tank so I don't get the laser pointer all wet. So I'm going to hold it outside the water, and I'm going to start at a very steep angle. So if we look at a normal line, normal to the surface of the water, this would be a very small angle of incidence. So we should see refraction there. And I want you to watch and see what happens as I increase that angle of incidence. Okay, so there we've got a small angle of incidence. I'm going to increase that angle of incidence. Okay, now you see a lot of red dots in this picture, but anyway, what I want you to notice is what's going on inside the water. So here you see the incident ray hitting the surface of the water. I increase that, and all of a sudden you see a nice reflected ray. Now you're going to have to take my word for it. Actually, maybe we can see this. Okay, yeah, if you look at Monica, right here, you see the refracted ray on Monica, all right? Now, when I increase this, as soon as we go to that reflection, we no longer have a refracted ray. This is total internal reflection. None of the light is leaving the surface of the water. It's all being reflected inside the water. And this is only going to work when we're going from more dense medium to less dense, or a medium where the speed of light is slower to a medium where the speed of light is faster. So there's total internal reflection.
All right, so we see that total internal reflection in a fish tank, but let's look at situations that are maybe a little more practical. Here are a couple sea creatures, sea turtles. They're pretty cool. You can see the reflection of the turtle in the surface of the water. And the fish, same thing. This is a reflection of that fish just on the surface of the water. So we're underwater looking at these animals, and we see the reflection from the surface of the water. Now, there's a lot of waves in the water, so can we see outside of that water? It's hard to tell on these. Let's look at the next one. I really like these pictures. So we're underwater in swimming pools in each of them. Let's look at this one first, the empty pool, very calm water on the top. So the depth of the pool is only like to this point right here. We see a reflection of the bottom of the pool. This is total internal reflection. Now, if we decrease that incident angle, so you saw in the demo where I decreased that angle and then we got refraction. We had to increase that incident angle to get the total internal reflection. So if we decrease that incident angle, that means we're going to look up higher in the sky. Now we can see outside the pool. These are the lights in the pool arena, pool, whatever it is. I don't know what it's called. But these are the lights inside on the ceiling there. If we look down, if we increase that angle, we get to a point where it's total internal reflection. We don't see anything outside the surface of the water. This is going a little reverse in the demo. In the demo, I was shining the light essentially in the water, and then it was going out into air. Here we're having light coming out from the air and into the water. That pathway is exactly the same, it's just going the reverse direction. And then here's another image. We've got the swimmer here, we're underwater, and then we can see her reflection on the surface of the water, again, total internal reflection. Now, if we decrease that incident angle, we look up higher here, now we can see outside the pool. That's pretty cool. All right, so let's kind of look at how this works. Okay, in the first situation, we have refraction. We've got the incident angle is less than the refracted angle. We're going from a slower medium to a faster medium. And I said that in the video, that is key. You have to be going from an area more dense to less dense because you need the refracted angle bending away, or the refracted ray bending away from the normal. It doesn't work if it's bending toward the normal. Now, so we have refraction here. We're going to keep increasing this incident angle. We're going to eventually get to a point where this refracted angle gets to 90 degrees. Once we're at that point, this incident angle has a special name, and there's going to be a certain degree for, this set of two media here. It's going to be a certain value, but it's called the critical angle. It's that threshold. Anything less than the critical angle, and you're going to have refraction. At that critical angle, you start losing that refraction, and that is when the refracted angle is at 90 degrees. Now, if we keep increasing the critical angle, we get this total internal reflection. No refraction, it is totally reflected inside theta 1 equals theta 2. Okay, I should mention that in these others, we will have some light reflected as well. It's not very much. When you have it refracted, most of it is being transmitted through. A very small amount will be reflected down in. But once you exceed that critical angle, you have total internal reflection there. All right, so let's do an example here. What is the critical angle for light in diamond surrounded by air? So we have a more dense medium diamond surrounded by a less dense medium air, so it is possible to get total internal reflection. We're going to look at the critical angle situation, and that is when the refracted angle is at 90 degrees. So I've labeled this as diamond, this is where the light starts, this is air, that's the surrounding medium. So I'm going to say medium 1 is diamond, medium 2 is air, because we're going to use Snell's law here. So keep diamond on one side, keep air on the other. I don't care which one's on the left or the right, it doesn't matter. The index of refraction for diamond is pretty big, 2.42. If you remember earlier in this video, we talked about the speed of light in diamond was pretty slow relative to the other materials. So the index is pretty high, 2.42, we're given that. Index for air, again, we can use 1. So just plug in our numbers. So we have 2.42 sine of our critical angle, that's what we're looking for. And then on the air side, we've got 1 times sine of 90 degrees. Whenever you're looking for critical angle, your refracted angle is 90 degrees. Have to do an inverse sine again, but we get 24.4 degrees. Okay, so an angle about like this, 24.4 degrees. That means any angle of light bigger than that is going to end up being reflected inside the diamond and not come out. We'll talk more about diamonds another day. They're pretty interesting. All right, let's sum things up here. Refraction is due to a difference in the speed of light. Index of refraction is just the ratio of speed of light in a vacuum to the speed of light in that material. The greater the speed, the smaller the index of refraction. You must go from one medium to another at a non-90 degree angle. There has to be some angle. If you go directly from one medium to another, it'll change speeds, but it won't bend. If you're going from a faster medium to a slower medium, the light will bend towards the normal. If you're going from a slower medium to a faster medium, the light bends away from the normal. To calculate how much light bends, we use Snell's law. N1 sine theta 1 equals N2 sine theta 2. Total internal reflection occurs when the incident angle is larger than the critical angle. This is where all the light is reflected and none of the light is refracted. And this occurs only when you're going from a slower medium surrounded by a faster medium. Okay, That's it. If you have any questions, let me know.